Most people know that nothing outruns light, but they don't realize that's not just a rule someone wrote down. It's woven into the architecture of reality itself. And here's what that actually does. It traps civilizations in a kind of temporal prison. To understand why, you have to first understand what happens when you push against that universal speed limit. Let's build a mental model. Picture a perfect clock, not a wristwatch, but a device where light bounces between two mirrors. Each round trip marks one tick. Simple enough. Now imagine I'm standing still with my clock, and you're in a spacecraft moving at a substantial fraction of light speed. What would you see happening to my clock from your perspective? From your viewpoint, my clock appears to be moving away. The light inside it has to travel a longer diagonal path to complete its tick because the entire apparatus is in motion relative to you. That extra distance means the tick takes longer, so you observe my clock running slower than yours. But here's the mind-bending part. From my perspective, nothing has changed. My clock ticks normally. I feel no difference. So which one of us is correct? Could time actually be passing at two different rates simultaneously? Both perspectives are equally valid. This isn't an illusion or a mechanical flaw, it's a fundamental property of the universe. Time genuinely stretches for objects in motion relative to an observer. The faster the motion, the more pronounced the effect. And we've proven this. In 1971, physicists placed atomic clocks on commercial jets flying in opposite directions. When those clocks returned, they showed a tiny but measurable discrepancy compared to a clock that stayed on the ground. Moving clocks truly tick slower. Why don't we notice this in our daily lives? Because the effect is negligible at the speeds we experience. Driving at highway speeds, the difference is far too small to register. It only becomes significant when you approach a meaningful fraction of light speed, 186,000 miles per second. For context, our fastest rockets today crawl along at maybe 30,000 miles per hour. We're not even close. But let's imagine we could build a ship that reaches 95% of light speed. Suppose we aim for a star 10 light years away. From Earth's perspective, the trip would take about a decade, but for the crew aboard the ship, time would be moving much slower. At 95% light speed, their clock runs at roughly 1/3 the rate of Earth clocks. So while 10 years pass back home, only about 3 years elapse on board. When they return, they've aged 3 years, while everyone they knew has aged 10. This isn't science fiction, it's the twin paradox, a direct consequence of Einstein's special relativity. It reveals that time isn't a universal constant. It's relative, dependent on how fast you're moving. Now here's where this becomes genuinely unsettling. If you're on that ship heading to a star 10 light years away and you want to radio back that you've arrived safely, what happens? Light signals travel at light speed, the same speed as your ship. From Earth's perspective, you arrive after 10 years. Your message then takes another 10 years to return, 20 years total. The people you're trying to reach have aged significantly. Your transmission lands in a world that has moved on. But it's worse than that. Suppose Earth detects a course error and tries to send a correction signal while you're still accelerating. They beam a message at light speed to catch up, but you're already moving at nearly the same velocity. If they wait too long, that signal will simply never reach you. You've outrun the sphere of causality. What does that mean for any civilization attempting to cross the stars? It means you become isolated. You're moving so fast that effective communication becomes impossible. The universe itself imposes a hard limit. You can travel quickly, or you can stay connected, but you cannot do both. Now let's scale this up. Our Milky Way spans roughly 100,000 light-years. The nearest star, Proxima Centauri, sits about 4 light-years away. The Andromeda Galaxy is 2 million light-years distant. These are staggering gulfs. With current technology, even reaching a fraction of light speed is fantasy. But let's assume a civilization, call them the Arcturans, has solved the engineering problems. They live 36 light-years away and decide to visit Earth. They build a ship capable of 99% light speed. At that velocity, time dilation becomes extreme. For every year on Earth, only about 2 months pass on board. So while the journey takes 36 years from Earth's perspective, the crew experiences only about 6 years. They arrive youthful, but when they try to send a report back to Arcturus, that message will take another 36 years to arrive. By then, more than 70 years have passed since their departure. Everyone they knew is likely dead. Their home civilization has evolved without them. Any command structure, any supply line, any coordinated strategy, it all dissolves. They are, in a very real sense, alone. This is where the Fermi paradox comes into focus. The question, If intelligent life is common, where is everybody may have a sobering answer. The laws of physics themselves prevent interstellar civilizations from maintaining coherence. Every expedition becomes a permanent departure. Every probe is a one-way emissary. Now imagine thousands of civilizations across the galaxy, each facing the same constraint. They can explore, but they cannot empire build. A colony launched at relativistic speeds doesn't just travel through space, it travels through time at a different rate, severing itself from its origin. Some might imagine alternatives like wormholes or warp drives. These appear in Einstein's equations as mathematical possibilities, but they require exotic matter with negative energy density, stuff we've never observed and have no reason to believe exists. A stable wormhole would need to be held open by forms of energy that remain purely theoretical. A warp drive would demand bending spacetime on a scale that would require energy comparable to a star. Should we bet on solutions that require physics we've never seen? In science, we work with what we can confirm, and what we can confirm is that relativity is robust. The speed limit is real, time dilation is real. These aren't arbitrary restrictions, they're woven into the fabric of existence. Let's make this concrete with a scenario. A civilization 50 light-years away launches a robotic probe toward Earth at 50% light speed. The journey takes 100 years. The probe was programmed with knowledge from its launch date, but by the time it arrives, a century has passed on its homeworld. New discoveries have been made, politics have shifted. None of that context can reach the probe in time. If home sends an update signal, that signal will take another 50 years to arrive. The probe operates in a temporal vacuum, an ambassador from a past that no longer exists. This is the barrier I'm describing. It's not about engine power or fuel efficiency, it's about the structure of space-time itself. The universe seems designed, not literally but effectively, to keep civilizations isolated. You can have a thriving local system, or you can send out seeds that drift beyond contact, but you cannot maintain a unified interstellar network. Some futurists speculate that advanced beings might transcend biology altogether, uploading consciousness into immortal machines. But even then, the speed of light remains. Real-time coordination across light years remains impossible. Two colonies separated by distance will inevitably diverge, their experiences and cultures drifting apart because causality itself operates on a delay. What would that feel like for a species trying to expand? It would feel like a universe designed to prevent cosmic empires. Every new settlement would eventually become its own civilization, effectively orphaned from its origin. This suggests a resolution to the Fermi paradox that's both simple and profound. We don't see aliens everywhere because the galaxy is vast and physics is unforgiving. Any civilization is essentially confined to its stellar neighborhood. They can't sprawl across the spiral arms without losing the very connections that make them a single civilization. The cost of crossing light years is the loss of home. Now what about us? If we ever launch a crewed mission to another star, we must accept that those voyagers will be on their own. We can't rescue them. We can't give them updated instructions. Their descendants, if they arrive at all, will reach a world that has moved generations beyond the moment they left. This is why some researchers discuss generation ships, vessels where entire societies live and die in transit, with children and grandchildren inheriting the mission. It's possible. It doesn't violate physics. But it's also profoundly lonely. The culture aboard such a ship would be shaped by permanent separation, a drifting world unto itself. When I reflect on these constraints, I see something strangely beautiful. The universe is immense and likely teeming with life, but its fundamental rules create a kind of cosmic quiet. Each pocket of intelligence occupies its own bubble, moving through time at its own pace, unable to easily touch the others. The speed of light isn't a wall, it's a horizon. You can approach it, but crossing it would require rewriting existence itself. And time, which we imagine as a steady river, actually flows at different rates depending on where you stand and how you move. This is the reality that limits civilizations. You can go fast, but you leave your origins behind. To reach the stars is to leave your own time behind. What this means is that any advanced species, no matter how brilliant, faces a fundamental trade-off. Move slowly and journeys take millennia. Move quickly and you become a temporal orphan. The galaxy, under these constraints, would be filled not with bustling empires, but with isolated outposts, each one cut off from its past by both distance and the relativistic stretching of time. This isn't a failure of imagination or technology, it's the physics of our reality. And understanding it changes how we think about our place in the cosmos. We're not alone because the universe is empty. We might be alone because the universe is structured to keep civilizations apart. If you found this perspective illuminating, consider supporting winds of thought with a like. It helps these deeper explorations reach more people. And drop a comment. If time itself bends with motion, what does that mean for how we understand connection?